We will begin with a presentation given by Leona Fan-Chiang, who has been a leading member of Lyndon LaRouche's scientific research team for a number of years, and who has written a number of papers on fusion power and economics. So without further ado, I would just leave the stage to Leona. That doesn't.
Okay, so we have actually addressed 3 of 4 laws that Mr. LaRouche has said that hasn't said, he has demanded, has to be law. And I'll go through them right now. But so since this whole, well, let's say this. According to the way that Mr. LaRouche sees the human society and the way that humans must develop, he has derived 4 different things that need to occur right now. One of them was Glass-Steagall. The next one was the credit system, which we've discussed. The third one we've sort of discussed now, which is using that credit to build. To actually build high energy density infrastructure and basic productivity. And the fourth one, which we have not discussed, which I'm going to get into today, is a science driver, specifically fusion with fuel from the moon. So now, I've gotten various responses on this. We've obviously gone into Congress and gone into states and various municipalities to discuss this idea. And as was mentioned earlier, fusion, as well as mining the moon, or specifically Helium-3, which I'll go through, is something that, 1, the United States has pursued, but 2, that the Chinese are going for and have put lots and lots of money into. Now, but I still get the question, why fusion? And especially from legislatures who like to think about money. Why should I spend money on fusion? We don't even know if it's going to work. At least I've heard that now from people who are well educated in various, for example, I went to a conference, a bunch of us went to a conference this week of nuclear scientists. So these are people who build nuclear reactors. And this is still the question. Why should we go for fusion? It's not, we don't even know if it's going to work. Are we just throwing away our money? And then the other aspect, of course, is we have so many problems. People are hungry, the healthcare system is collapsing, their roads are broken, and so on and so on. It seems infinite. Which one do you address first? Do you throw money at them all? This is where strategy comes in. This is sort of Mr. LaRouche's specialty, is strategy, economic strategy. How do you address all these things? Do you sort of just ignore them and go for one thing? At least you'll solve one problem. Now, the last time we had something like what Mr. LaRouche is proposing right now, in a serious way, at least in the United States, that people alive today can remember, is actually the Apollo program. So the Apollo program is a similar thing. Now, why should we pay for this? It's not going to work. In 10 years, or by the end of the decade, that's not going to be possible. There are all these doubts. And what we saw from the Apollo program was a total transformation. And people don't, there are some things that are really hard to measure for anybody who's taking in economic statistics or anything like that. One of the hardest things to measure is how far your society is thinking ahead. And yet, that determines everything. It determines society is acting at any one moment. And one of sort of the results, the shadow of this, was that when Kennedy made his speech, so this is before any investment actually goes out, individual companies started to invest heavily into their R&D. So R&D, research and development, it's not overnight. It's not money you're going to get back right away. It's not even something that you know is going to work. So in some sense, it's are you throwing money into a hole? It's a similar thing. But they knew it was going to go somewhere. They had a sense. They had a sense specifically that there was a mission for humanity to evolve. And that's really what Mr. LaRouche is calling for right now. It's not getting rid of these problems. These problems are actually created by the fact that we have not evolved. That when we were supposed to continue to develop as basic nature of the human species, we did not. And if you sit back and reflect at most of the problems that we run into today, it becomes really clear. Most of the problems we have today are absolutely solvable. There are no impossible problems, really, that you can think of. There are problems which you have not thought of, which are very difficult, which I'll go through some of. But most of the problems you can think of are absolutely solvable. Even some of the hardest ones, like poverty in Africa and things like that. Okay, so I'm going to go through, first of all, what is fusion, or a review for all you fusion scientists out there, which most of the United States or in Canada are not, unfortunately. And then we'll go back to this problem that I'm talking about. Okay, so fusion as a concept is actually pretty simple. It was conceived in the early 1900s, before fission actually, so before nuclear power, so what we know as nuclear power today. People had conceived of fusion. And it was thought that fusion would occur first. And it turned out to be more difficult than we thought. So fusion is taking two elements, two atoms, and fusing them together. That's pretty much it. Fission is taking a larger atom and splitting them up. Okay, so what I'm showing here is sort of the textbook version. And you'll see these in textbooks, sort of gumball drop like atoms that come together somehow and create two other atoms. Now, I'm just going to get you familiar with the terminology. Tritium is a form of hydrogen. Deuterium is a form of hydrogen. These are two forms of hydrogen, meaning if you breathe tritium or deuterium, actually tritium you will notice, but deuterium, for example, or if you breathe just regular hydrogen, you will not notice. To us, to the chemical world, this is all hydrogen. To the nuclear world, this is like a salamander in a rock. They're very different. So, how do they differ? Technically all they differ is by weight. They only differ by weight. So deuterium is a heavier hydrogen, and deuterium is yet a heavier hydrogen. And yet together, they come together and create helium and a neutron. So this is a nuclear process, right? Meaning two nuclei, two elements are coming together and creating two different elements. Not a chemical process, not a sort of a burning process, completely different. And I just want to emphasize again, on this scale, things that made no difference at all become very, very important. And also things that we thought were important have a different significance. This is also something that is usually used to argue for fusion. So this is energy provided per pound of fuel. So you see wood, 1.9 kilowatt hour per pound. Coal, much more than that. Petroleum and other fossil fuels, like natural gas mainly. Again, more than that. And then you move into the nuclear domain. So uranium, fission, nuclear power plants. Literally 1,000,000 times more. So it's one of those things you say, 1,000,000 times more. No, this is literally 1,000,000 times more. Deuterium, that's the one we were just looking at. A fusion fuel. 4 times more than that. And there are some factors because uranium fuel is actually only 7% burnable fuel, but that's just technicalities. But you get a sense of the order of magnitude of energy. And this should already show you that we're entering a different domain. So that's generally the argument. I mean, basically the argument for why people mostly argue for fusion. Now I want to get into something else. So this is how I want you to think about fusion and why Mr. LaRouche is specifically saying that we need to push fusion as a science driver. Why specifically that, not mining the depths of the earth or something like that? So this that you're looking at is a huge blown up of something that's about the size of a pencil eraser, so about that small. And it's obviously a cartoon version. This is a portrayal of 192 lasers shooting at a little gold capsule the size of a pencil eraser. And inside that capsule is a little tiny cryogenically frozen piece of fusion fuel. And this is a very early plan, or this was conceived pretty early on. Now, this is at Livermore Laboratories in California, Northern California, in the United States. So this was actually originally conceived as a way to replicate a controlled version of the bomb, the nuclear bomb. So we know fusion works. We did it before. It's a little messier when we did it that way. But the idea was, okay, well, let's take what we normally do. So for people who don't or not look at it, the way a fusion bomb works, or had worked, I guess it still works that way, is you take a fission bomb and explode it around a fusion fuel. So you sort of bombard the fusion fuel, and then you get fusion. So we know that works in a very, very large way. And this was one of the first ways, not the first, but an early way to conceive it. Okay, well, we can do fusion this way. Now, in order to do this, they've had to construct this apparatus, which, like I said, is 192 lasers. This lab has created some of the strongest lasers in the world. And they've condensed this piece of fusion fuel to 1,000 times that of lead. Now, if you give sort of, what does that mean? That seems like a lot. I'm sorry, it's 100 times that of lead. To give you a sense of it, the density in the sun of anything, the core basically, is 150 grams per centimeter cubed. This thing goes to 1,000 grams per centimeter cubed. Okay, this is a different reactor. And what you're looking at is plasma. So plasma is not something you deal with on, actually it is something you deal with on an everyday basis, but not this kind. Plasma is a state of matter. So you have solid, liquid, gas, then you have plasma. And plasma is what you get when you are able to strip the electrons off of something. And it is, well, we normally encounter it in lightning bolts, in fire. Flames are a low temperature version of plasma. And if you take a magnet to it, if you take a very strong magnet to it, you'll see some difference. So what this is that you're looking at is a toroidal shaped, it's called a tokamak, which is just Russian for donut shaped. A toroidal shaped magnetic field. So what they figured out is that in order to get fusion, they need to have this plasma at 100 to 150 million degrees Celsius. Now what does that mean? How hot is that, right? Sort of like quadrillion numbers. To give you a sense, the sun, again, is one of those things, when you think hot, you think incinerate everything, you think of the sun, right? So the sun's temperature ranges, depending on if you're on the surface of the core. The sun temperature ranges between 1 and 27 million degrees. So this thing here is 100 to 150 million degrees. And there's another device, another apparatus, which I don't think I have a picture of, which goes to 1.2 billion degrees. Now, like I said, these are temperatures that don't even happen on the sun. And this particular one, I think this one is in the UK, but there's one in San Diego, there's one at Princeton, there's two in China, and so on. So these are little stars of our own. Here's one, this is east, this is the one in China. This is one of the most advanced ones, because they use superconductive magnets. So these are magnets which have been cooled down so much that they hardly have any resistance or produce any heat. This is another one that's just a sort of radical picture of it. But this is a sort of swirly version of it. One thing I want to point out, the reason actually I have this picture is that while we've been working with these high temperature plasmas, for example, they have been showing us that what we think we know about physics is at the least incomplete. Because according to all of our, we should know electromagnetism, gravity, and between all of that, we should be able to calculate what's going on. That has not happened. Instead, very particular, for one, we have not been able to forecast what these things do. And two, the way that we've been able to control these things, to be able to control plasmas, has been only by working with it. So we found that it likes to do certain things we didn't previously know, and one of them is this. So when this is actually those donuts that are twisted? I don't remember what they're called. They're twisty donuts. Yeah. Anyway, it's kind of like that. And so they found out that if you shape the apparatus to that, well, first of all, in the tokamak, it likes to do this. It sort of likes to twist. That's what the plasma likes to do. And then if you shape the apparatus to what it likes to do, then the plasma thinks it's going straight. So this one is in Germany. I'll come back to this one. This is a picture of another type of apparatus. Okay, and this is the last one I'll go through as far as these reactors go. This is a schematic of a laser that was designed for the first one that I showed you, the laser fusion. Now this laser acts at first of all, it acts at a quadrillion watts. Now I know that's a lot. I didn't actually come up with a good example. It is, though, brighter than any star that we know. Now, by an order of magnitude. Now, it only acts at this brightness for a quadrillionth of a second, which is how they were able to produce that much power. Now, what is a quadrillionth of a second? A quadrillionth of a second is about the speed that chemical reactions occur. So with this laser, at that type of speed, you're able to probe what is happening on the chemical scale, on the scale that chemical reactions are occurring. So for example, one of the things they can do is they can blast a sort of a cloud of atoms, blast all of their electrons off. Before the atoms realize that its electrons are off, it collects something. You can shoot another one at it and fuse them. Now this is a schematic of a particular experiment, which is they shot laser at the surface of gold, accelerated the electrons from the gold, which then create gamma rays. These two, and some of this, I'm not going to stop and go through. It's not incredibly important, but for people who know these things. These are two antimatter pairs. Then they were able to get this excitation to knock a neutron off of gold and create fission from uranium. Now this is all in about 2 inches. This is a gold plating, gold thin molecular thickness gold. They're able to accelerate electrons to relativistic speeds in about 2 inches. Now one more thing is, let's see if I have that here. Okay. So I just want to get you a sense of what fusion actually means, to me at least. And I think the way that Mr. LaRouche is really looking at it, it's not just more power. More power is very important. Power limits a lot of the things that I think people in more developed countries don't really realize it. Power limits a lot of things we do. But it is actually a higher control. You're seeking a higher control of the universe, a higher understanding and then a more advanced relationship between human beings and the rest of the universe. That's what you're looking at. And when you deal with these type of problems, for example, in this case, fusion, you really are challenging all aspects. And that's really what you want. Now let's get to application. So this is a schematic again, like I said, of this is a schematic of a fusion torch. Now this is conceived of. There were several papers written in the 80s, early to mid 80s, and the idea was to take these hot plasmas and does anybody know the melting temperature of iron? You?
I don't know this. I used to know it, I forgot. What was it?
Ballpark?
Around 2,000 or maybe 1,600 degrees Celsius.
Yeah. Ballpark?
I don't know. It's a guess.
think he's right, because I remember the documentary about 9/11, the melting of steel.
Yeah, what was
And at the
the?
fuel that a plane explodes, doesn't even come close to the temperature that steel needs. So
Correct.
I think you're right, it's about 2,000 plus or
Wow,
something.
considering my goldfish memory. Is that right?
So, yeah.
It reminds me of Mr.
It's
Fusion,
about
sorry.
3,000, 2 to 3,000.
Back to the
Yeah,
future.
and when you run a boiler to burn fuel, you know, it'll get up to 3,000 degrees F, that's about 1,500 C if you cycle the firing, and you can do it in steels, which tells you that steel doesn't help, so your probably numbers are pretty realistic.
So now, most materials, almost any material that you're going to deal with melts at thousands of degrees. Let's give a big ballpark at thousands of degrees. So most things melt before 3,000 degrees. There's a couple of things that will melt a little bit further. But at 27 billion degrees, like on the sun, or at 100 billion degrees, like in these reactors, nothing survives as a solid. So everything breaks apart into its constituent elements. So the idea at that point was, take this plasma, it's still magnetically confined. Oh, I don't think I mentioned that part, but this plasma cannot touch the sides, because we don't make material that can, same thing. Plasma has gone through, and you're placing solids into this plasma. The solids get disintegrated pretty much, and then it goes into separation. There's several ways to separate it, which I'm not going to go into. You can take it up in question and answer if you want to know. But basically, you're taking anything that you want and making it into its constituent elements. And then this is just a pedagogical. So if you take a cubic mile of dirt, an average cubic mile of dirt, so you take I took the United States. You take the United States and average the land there. Take the average cubic mile of dirt and you were to process it in this form. You would get 200 times the annual production of aluminum, 8 times the annual production of iron, 6 times the annual production of zinc, and 100 times the annual production of tin. Now you probably won't be putting dirt into this thing. You may. You probably won't. Likely, actually, one of the great resources may be landfills.
Coal ash.
Basically, anything that comes from human society as trash likely has things that human society uses. And so, but it should give you a sense already that this already redefines what we think are resources, what we think are ore, what you call ore. No, I'll do that later. Okay. Actually, I'll go through this. So this is actually a picture of a piece of metal that's being cut with a conventional laser. So we do use laser for machining now. It's very cool. And then that laser that I showed you earlier, that's what it cut. And to get you a sense of this, this laser acts so fast that they can do surgery with it, such that it can incinerate a cell and not have any other cells next to it notice. So this is true laser surgery. This is on a piece of metal, similar. This is so fast that the material next to it does not heat. Does not notice at all. As opposed to this one, which after you cut through it, heated, it melted it. So that should give you a little sense of the industrial revolution between the laser cutting and the plasma processing. Okay, how much time do I have now?
Go to 5 minutes.
Okay. Okay, so now I specifically want to go through helium-3, and this may go a little fast. So, Mr. LaRouche has specifically been excited about China's announcement that they want to go to the moon and mine helium-3 for fuel for fusion. And this crowd doesn't have that same reaction, but the nuclear community often has this funny reaction, which is, why do you want to go to the moon? You can do other things here. And my usually reaction is, it's because I want to go to the moon. So whether you want to look at it as you need helium-3 for fusion, or whether you want to look at it as you want to go to the moon anyway, and it would be great to get the helium-3 off the moon to use it, I don't care. But helium-3, it's a form of helium. Like I said at the beginning, helium, helium-3, between helium-3 and helium-4, which is the one that is most common, if you breathe it, if you put it in your balloons, it's all exactly the same. To the nucleus, it's not. So these are actually 4 different ways of producing fusion. The top one is the one I showed you earlier. And I'm not going to go through all these. I'm just going to show you the top one and the lowest one. If you see in the right side, the little stars areas give you how much power comes out of these 2 reactions. And you'll see the highest ones are the top one and this one. This one turns out to be harder to do, deuterium and helium-3. So this is a form of hydrogen and a form of helium. This one turns out to be harder to do. You need higher temperature and so on, but more desirable because, okay, so now it's sort of replaced this one here and the top one are the 2 we were just looking at. So I broke them apart. The top one has this little N. So the top reaction comes out with, so you put in 2 forms of hydrogen. You get out a helium and a neutron. Neutron is just a neutral particle. And neutral particles are very interesting. They're great for some things and terrible for other things. And the reason that they're terrible for other things is because they are neutral. And so they are unaffected by magnetic fields, for example. And has anybody here heard of ITER? Heard a couple people here? It's a huge fusion reactor that's in France.
Oh, yeah.
Anyway, part of why it's so huge is that when it starts operating, it will be radioactive. And so therefore, they've had to put in a lot of automatic things and shielding and so on. This helium-3 reaction puts out most of its energy in this aspect. A proton is actually just hydrogen, basically. So it puts out most of its energy in a form of hydrogen. It's charged, it can be controlled, and you can easily produce electricity from it. So, this is a nuclear power plant. People who don't know those, have people ever seen those pipes, those things with the steam coming out? So usually people use it as, the cooling towers. Usually people think that something is coming out that's very dangerous. It's actually just steam. So this is a nuclear power plant. Nuclear reactions are happening here. Neutrons are coming out. When neutrons get into the water, they heat up the water. The water then heats up other water. Water becomes steam. It goes through a turbine. Then you just got a steam engine. Okay, regular old 200-year, 160, 20 years, or 150-year-old technology, okay.
But it's efficient.
It's 30%, 30 to 50% efficient. Right now, what's being produced right now out of this reaction here, the top one, is same thing, neutrons, just like fission reactors. And we would have to run it through one of these, basically. The difference, this is one difference, this is sort of a technical one. If you don't understand it, it's okay. This is, when you use helium-3 and, so a helium and a hydrogen atom, a deuterium, you get, instead of a neutron, you get a charged particle, and that charged particle, people know what electricity basically is. Electricity is moving electrons, right? So you have in here already a moving proton, sort of an anti-electron, you could say. So you can actually directly get electricity out of this. No conversion into steam, no conversion into sort of a mechanical process. Not a 30 to 50% efficiency. It's not burning like in your car. It's just directly turning into, it basically is electricity. This is just a funny picture, which is a coal reactor doing exactly the same thing. Okay, so helium-3. Has anybody ever heard this term before? Before you ran into a table or us? Raise your hand if you've heard of helium-3. Okay, so just a couple of you, okay. So helium-3 is something that most people in the world probably had not really thought of, and probably still aren't thinking about. And yet it's become one of the most valuable things in the world. And one of the things that has pointed out is that the most valuable things in the world, which people thought were valuable, like the entire debt bubble, has negative value at this point. And things that had no value or weren't even thought of before have become of the utmost, the highest value, like helium-3, which prior to this was dust. Just dust on the moon. We've got dust here, right? Why do we need dust on the moon? But it is in this day in which the other people have pointed out that in the time where this whole shift is occurring between the BRICS nations, between Argentina and Egypt and Bolivia and all these countries who are now saying, oh, this weird twilight zone we've been living in is I think it's over. In this period, you do have a redefining of value. And the role we have here is to play a really crucial role in defining this paradigm right now at the highest level. Not just, okay, let's bring everybody to have a great living standard. Really, the way that you're going to get people to a good living standard is we have to redefine what we think about, what we think human beings are. And that's really what the role of a science driver is, which is why, of 4 points, one of them is a science driver. That's how you're really going to get at all of these different, if you change the way that human beings think, or what human beings think they can do, like, for example, make a little star of their own, or be able to go to another star in a fusion rocket, and things like that. Other things become actually very, very simple. Believe it or not, you can desalinate water. That's not a problem. You can, you can perform surgery on these scales and so on. Those things are actually not that hard. But it really is, I would say that's gonna break the bone of, or break the, what's that term, that phrase? But it's gonna be the turning point of this whole process. It's not gonna be any particular law, but it is gonna be, how do we see ourselves? And how do we change, how do we advance that view of ourselves? And then how does that reflect into the economy and all the things we do? So I'll just end there.
You're good, you're 5:01, so you have 10 minutes to ask questions to Leona. And then afterwards, there will be a caveat where we will be able to have a longer discussion at another location, which I'll announce at the end. But, Al?
Yeah,
I have a question on chemistry.
on chemistry.
When you're talking about, as you almost in your first slide, that deuterium and tritium react together to form helium-3 and a neutron.
Yeah.
When you put these into a reactor for fusion, are they present as the deuterium and tritium, or are they present as deuterium oxide and tritium oxide, which then react and you form helium and a neutron, and then you would get oxygen out? Is that correct?
No, they have to produce the plasma first. I mean, they have to produce it pure.
So the plasma would break apart
They're putting, yeah, pure.
but it would start as deuterium oxide or tritium oxide, is that correct? And then you put it into a plasma reactor, and out the other end comes this stuff?
It depends. Like for example, at the NIF, they have a cryogenic frozen deuterium, I'm pretty sure. I don't think it actually is a, yeah. I think it sort of depends on which reactor you're talking about. Sorry.
Oh, great. Yeah, just speaking of the chemistry behind these reactions. See, the thing is that it takes a given amount of energy to break a bond, a chemical bond, whatever kind of bond it is, be it single up to triple, it doesn't matter. The energy in these reactors is more than, definitely much more than sufficient to break those bonds. So yes, you'd actually have pure elements fusing without electrons around them to form new nuclei. And about chemistry, chemistry concerns itself with the behavior of electrons around an atom, whereas this field of nuclear science concerns itself with the nucleus of the atom, and it negates the impact of electrons to a large degree.
Right,
They're actually two parts of the same coin, because they both actually explore the dynamics of the atom. There's one of those on the surface, the other one's more deep down.
Thank you.
Yeah.
Okay, I believe we have a question from Montreal. Oh, and then we'll ask Dr. Hussein.
Okay. Go on.
Hi, Leona.
Hi.
Great presentation. Thanks a lot. I had a question among the many detailed questions I could ask. Rather, you guys were at this nuclear conference. I wanted to know, with this kind of idea that we kind of went in there to try and elevate the discussion, if you had any interesting anecdotes, the reaction, reception of the different folks at this conference. If you had anything to say on that.
I thought one of the most interesting and maybe not the most exciting reactions was that I sort of thought that nuclear scientists, and especially nuclear scientists from China, would be excited about helium-3 and fusion and so on. But there were some people who were excited about fusion, but there was still practicality, which is, why, some of these questions I was asking at the beginning actually got this week, which is why should we go for fusion? Is it ever going to work? Is it, and so on and so on. And what I had to go through with them was that, it's like going to the moon. Is the most useful thing we got out of going to the moon the fact that we stepped on the moon? Believe it or not, that question has a funny answer now. But at that time, no. At that time, the most useful thing was the fact that we had to a human being outside of Earth's atmosphere or Earth anything, we had to increase precision of all of our machine tools down to hold the machine tool, which meant then people who do machining, the machine tools are the machines that make all other machines. So meaning all other machines are also much more precise. People don't know most of our medical technology came from that era and from nuclear technologies and so on. But that's what you get out of it. But anyway, so I had to go through that kind of stuff with them, which I thought that we wouldn't have to. But we also brought it, yes, we did also bring in the political discussion when it was not being had. So we're not allowed to.
Well, I have one question from,
Yeah, well, anyway, I want to go first.
sorry,
No, I'll go last.
do you have a question?
Actually,
That'll probably be the last question before
it's
this.
not a question, it's a comment.
Or a comment.
I'm a nuclear physicist,
Oh, good.
and talking on behalf of the nuclear physicists, I don't think any nuclear physicist will tell you we shouldn't spend money on fusion. If someone will say that, they really don't know the realities of the energy situation. However, the important thing is that the world and the universe is running on minimum energy and conservation of energy. Any process that doesn't follow these will not work. And for any energy source to be viable, you have to compare the energy you get from that source compared to the energy you invest in getting that source to work. So the sending something to the moon to collect helium-3 and bring it back to Earth to use it to helium-3 fusion will make this energy returned and energy invested to completely negative time. The helium-3 is extremely difficult to do. It requires very high energy, high temperature, and without that high temperature, it's not going to work. The temperature is over 1 billion degrees compared to the deuterium-tritium fusion. And the deuterium-tritium fusion so far is not successful, hasn't been successful so far. The control is a big problem.
Right.
However, the world didn't give up on it. The ITER program in France, there is allocated already $40 billion for it. In addition to the fusion, laser fusion programs, the United States are taking also other billions and billions. So the world is not giving up on fusion.
Right.
Even though 60 or 70 years of research and billions of dollars spent already were unsuccessful. But still, this is the ultimate source of energy and we should really pursue it.
Yeah.
The question is, when it's going to happen? We don't know. So right now, planning for an economy based on fusion, I think that is not possible because we don't know when that fusion source is going to be available. So what do we do in the meantime? This is really the big question now, especially with the situation of the fossil fuels and the destruction it's doing to the environment.
Yeah,
So the picture, the over-optimistic picture of fusion could be dangerous for the near term.
I think
Long term maybe, but not many.
I actually think you missed the point of my presentation. Because I'm not saying that we should wait for fusion. That's not what I'm saying. I'm saying that the fusion power is not the reason we fund fusion. It is in the long run, yes. But that we can see that in the process of funding fusion, many other things have been driven. Now, I think in the meantime, we should use fusion neutrons to breed fission fuel. That's a possibility. We should build a lot of fission reactors actually right now. That's something we can do very quickly. China is building 25 reactors right now. They plan to finish them by 2020. They plan to triple their capacity by 2020. That's something we can do. We could build 25 reactors here if we wanted to in that time. Or not, maybe not in that time. We can. So there are a lot of things we do. I'm saying the reason that this is what I'm saying is that a lot of people sort of talk about fusion from the standpoint of the end goal. But it is like the Apollo program. It's not the end goal. That's the main point. Yes, that end goal will drive us somewhere. will lead us somewhere that's incredible. But the process of seeking something that's sort of impossible does a lot. It does actually a lot for everything. Yeah. But yeah, I think you're right. The other thing about the moon, it's funny that you say that about Helium-3, because I got that same reaction out of the entire nuclear community. You know, that's what I meant at the very beginning, is that, look, we go to the moon because we want to go to the moon. Yeah, that's really honestly for me, that's the real reason. And then, yeah, the other thing is, you know, we're going to need fusion on the moon. So bring it back to Earth, we'll probably have to do that to do basic research and things like that. Honestly, I think we're going to need we're going to need a power source in developing space. And that would be a great start.
Yeah, well, I would just, we've reached our time limit for the Q&A for now. There will be opportunities to have a dialogue.
I'll yield my time, let him ask the question.
Okay.
Yeah.
Oh, yeah. I've heard that some articles have been saying that the end of the world will happen. Some articles say that, but it's not true. I keep hearing that, but some people are getting tired of hearing end of the world all the time sometimes, especially movies.
Give up.
Yeah, but it's not true.